Voronoi Rooms. Dynamic visibility modulation of overlapping spaces for telepresence. We propose a multi-user mixed reality telepresence system. Our system starts by overlapping users' spaces statically to maximize the shared space. Then it dynamically modulates the visibility of each space based on users' locations to ensure that each user's action is clearly visible to others. This is the overview of our method. We first scan the physical spaces to obtain their 3D models. Then 2D floor plans are extracted from 3D models. The spaces undergo an optimization process to maximize shared empty space for all participating spaces, followed by object augmentation. In the MR system, non-shared spaces are split in real time based on Voronoi regions for visibility modulation. Let's see the detailed procedure of how the visibility is decided. First, once the boundary between the shared and non-shared space is computed, it is given as input to the system. Inside the shared space, each user's local physical space is directly visible through the head-mounted display's pass-through feature. For the non-shared space, the Voronoi diagram determines which areas of the rooms to visualize. For regions outside the shared space, pixels are rendered according to users' corresponding Voronoi regions. The remaining spaces, the shared space and the local space that are not occupied by the visible regions of the other spaces, are shown as pass-through. As users move, their positions update the Voronoi diagram, dynamically adjusting visible areas to reflect changes. This is a temporal moment of multiple rooms aligned and visualized. The area outlined in green represents the shared space where all users can move freely without colliding any obstacles. From each user's perspective, this shared space appears as their own space. Beyond the green line, the visibility of the three spaces changes dynamically. Our dynamic visibility modulation updates the Voronoi partitioning of the spaces as the users move. This video shows the visible parts of other spaces augmented within each MR space. Physical spaces are not shown here as they are presented to the user through video see-through. Examples of overlapping more than 5 spaces. The top row shows an example of 5 rooms participating in telepresence, as seen from a room on the left, and the bottom row shows an example of 8 rooms in telepresence. While the spaces look more cluttered as the number of rooms increases, users are not constrained within the shared space and can keep interacting with others in the non-shared spaces. User evaluation. In the following scenes, we will demonstrate 2 conditions with 2 tasks each. 2 conditions are baseline, without non-shared space visibility, and hours, with non-shared space visibility. 2 tasks are an introducing spaces task and a block stacking task. The figure compares the visibility of 2 conditions used in our experiment from similar field of view. The center column shows top-down views of the environments. In the baseline condition, only the local user's space is visible, while in ours, 3 spaces are visible depending on the Voronoi region split. The right column shows the first-person perspective of user B. In Task 1, each participant introduces their space to others in turn. In Task 2, participants collect the assigned blocks and collaboratively stack them in a specific order. This figure shows the spaces used in our user study. In the baseline condition of Task 1, user A is explaining the blue space to the other participants. In the baseline condition of Task 2, participants are stacking blocks in a specific order. Participants and blocks disappear when they are located outside the shared space. In the R's condition of Task 1, user A is explaining the blue space. In the R's condition of Task 2, participants are stacking blocks. Participants and blocks are visible even when they are located outside the shared space. Thank you.